And I'm going to talk about local ill-posedness, global ill-posedness, instant blow-up, finite time singularities for the surface quasi-geostrophic equation. I will give a survey of what is known, and I will announce, present a new result with my PhD student, with Martin. Okay, so the surface quasi-geostrophic equation. This is an equation in dimension 2. We're in the plane. The unknown is a scalar function, theta. Theta is transported by the flow, and the velocity of this flow is divergence free. It's an incompressible fluid. And so we can write it down as the gradient perpendicular of the stream function, and the relation between the stream function and the scalar theta is given by the square root of the Laplacian. So if we can invert the square root of the Laplacian, take the gradient perpendicular of the stream function, and we can write down the velocity as an integral operator with respect to the unknown theta, and this gives us the Riesz transforms. The singular integral operators is a convolution of theta with a kernel, a Calderon-Simon type kernel. And so this model, the surface quasi-geostrophic equation, come from a geophysical context. The 3D quasi-geostrophic equations model the dynamics of big masses of air in the mid-latitudes, where the Coriolis force plays an important role. And by taking a specific initial data, the action, the dynamics happens at the boundary, at the surface, and this dynamics is given by the surface quasi-geostrophic equation. And SQG has been used to describe the formation of fronts of hot air and cold air, and this phenomena is known as frontogenesis. So, but it was in 1994 where Peter Constantine, Andy Maida, and Esteban Tabac realized that this was the SQG was a very good model of the 3D Euler equations, where the vorticity for 3D Euler plays the role, or the gradient perpendicular theta plays the role of the vorticity. So in the case of 3D Euler, the vorticity is equal to the curl of the velocity, and the vorticity satisfies the equation. This is the derivative along trajectories equal to the gradient of u applied to the vorticity. If you compare this with SQG by taking the gradient perpendicular of the equation, what we get is that the derivative along trajectories of the gradient perpendicular theta satisfies similar equation than the vorticity, where the gradient of u is a singular integral operator with respect to the vorticity in the case of 3D Euler and to the gradient perpendicular theta in the case of SQG. They not only they have similar, they satisfy similar equation, also they have, both of them have the property that the energy, the L2 norm of the velocity, is conserved in time. And also, in the case of 3D Euler, the vortex lines, which are tangent to the vorticity, move with the fluid. In the case of SQG, the level sets of theta, since theta satisfies a transport equation, the level sets move with the fluid and they are tangent to the gradient perpendicular of theta. But SQG has more conserved quantities than 3D Euler, since the transport equation, one can multiply by powers of theta and then integrate. The nonlinear term disappears because the velocity is divergence free. And what we have is that all LPs of theta are conserved in time for p bigger or equal to 1 and up to infinity. And that gives us bounds for the velocity. In particular, the L2 norm is conserved, but also we get bounds of the LP norm for all p's between 1 and infinity. And this is because the velocity are the Riesz transforms. The equation, this is the equation I wrote for the gradient perpendicular of theta. And if we, in the left-hand side, what we have is the derivative along trajectories, and in the right-hand side, the gradient of u is a singular integral operator of the derivatives of theta. So that what is telling us that maybe the derivatives of theta, the gradient perpendicular of theta, satisfies an ODE of this sort, and that implies possible finite time singularity for SQG. Okay, so we're going to consider the initial value problem. So we have an initial data in certain space. If this space is a Sobolev space, and let's take S HS, let's take S strictly bigger than 2, then Peter Constantine, Andrew Ryan, and Tabak already proved that the problem is locally well posed. Okay, so there exists a solution for a short time, and this solution is unique. If we only consider L2 as our initial data, then we have a solution globally in time. And this was proven by Resnick in 1995. And uniqueness here is a big open problem. If we consider L2 intersection with CK gamma, so Helder spaces, and K is bigger or equal to 1 and gamma is between 0 and 1, then Yahong Wu in 2005 proved that the problem is locally well posed. Okay, so questions that arises. So in those cases in which we have local well posedness, HS for S bigger than 2, and Helder spaces, do we actually have global existence, or there exists a certain time, finite time, in which the solution leaves the space? So that will be a blow-up. But we can also ask other questions. For example, in the case of HS, if S is bigger, smaller, equal to 2, initially our solution is in that space. Does it remain in that space? Or we could ask, if we have Helder, local well posedness for Helder, what happens if we take gamma equal to 0? So we're considering initial data, which are CK. Does the solution remain in CK? So these are the 3 questions we are going to discuss in this lecture. But before I go to classical solutions, let me give a brief description of what we know about weak solutions. So as I mentioned before, we know that we have global weak solutions in L2, and these were extended by Marchand in 2008 to the class of initial data in LP for P strictly bigger than 4/3. Then in the case of non-uniqueness or uniqueness, There's the recent work by Tristan Buckmasters, Steven Scholar, and Vlad Bicol in 2019, where they prove non-uniqueness for a weak solutions, but in a lower regularity than L2. And here you have the exact spaces. But in the case of L2, it's still an open problem. Then we can consider patches. And these type of solutions are really interesting. And we have all types of behaviors. These solutions consist on dividing the space in two regions. In one region, the solution will take a constant value theta 1, and in the other region, it will take constant values theta 2. And since theta is transported by the fluid, the values, the constant value will move in time, and the dynamics happens at the boundary. Okay, the boundary will move, and the question is, if we have certain smoothness on the curve, do we have solution for short time? Does the solution remains unique, and does it remain in the same space, or does it blow up in finite time? So it was in 2005 where Jose Luis Rodriguez proved that these solutions, if the interface is C infinity, it will remain C infinity for a short time. Then Francisco Gancedo in 2008 proved that if the solutions are, if the interface is in Sobolev space HS S bigger than 3, then we have local ill-posedness. Then together with Gancedo, we prove that in this space, the solutions are unique. And recently, Gancedo, Nguyen, and Patel improved the spaces and got the optimal space, which is H2, 2 plus epsilon, in which they prove local existence and uniqueness. And for this scenario, there is a conjecture that the interfaces actually blow up in finite time. There are numerical evidence that you lose the smoothness, the curvature blows up at the same point where the interface self-intersects with itself. And this is open. And there's a work by Kiselev, Yao, Flatos, and Fritzig, where if you take an equation which is slightly more regular than SQG, and you consider, instead of being in the plane, you consider you're in the half plane, and the interfaces self-intersect with the boundary, then the problem is locally well-posed, but it also breaks down in finite time. Okay, but in the case for SQG, this is still open. And then there's another family of weak solutions by Algindi and Jiang, where they are merely ellipses continuous near the origin, and you have to add, in order this to be well-posed, locally well-posed, you have to add an M-fold symmetry. And global existence or finite time singularities is an open problem for this type of solutions as well. Okay, so let's go back to classical solutions. So we are in Helder with the intersection with L2, or HS with S is strictly bigger than 2. And the question is, do we have singularities or not? So there, Peter Constant, Andrew Maid, and Esteban Tabac prove blow-up criterion, which says that in order to have a singularity at time capital T, the integral from 0 to capital T of the L infinity norm of the gradient of theta has to blow up. Otherwise, there's no singularity at time capital T. This is equivalent to the Vilcatomaida criterion for 3D Euler, where instead of the gradient theta, one has the vorticity. And another geometric, and another criterion, this is a geometric one, in which you look at the direction field of the perpendicular theta, and if this remains litigious, then there's no singularities. And this is equivalent to the Konstantin-Pfefferman-Maida result for Euler, where one similar result is criterion, but instead of the gradient perpendicular theta will be the direction fields of the vorticity. Okay. So numerical simulations for SQG. Well, the first numerical simulations where some singular behavior seemed to happen was done by Peter Constantin, Andrew Maida, and Esteban Tabac in 1994, where the initial data was exactly this. And what they observed is that the gradient of theta was blowing up in finite time at this rate. Then 3 years later, Okitani and Yamada, with higher resolution and more powerful computers, they suggested that maybe instead of a finite time blow up, what happened is that there was a double exponential growth. A year later, Constantini and Scherthofer confirmed the numerics of Okitani and Yamada and gave a more precise numbers on this growth. And then in 2012, a group led by Peter Constantin and Yahong Wu continue with much powerful computers, continue the solution, and at some point the solution stopped growing. So the gradient of theta became bounded stopped growing as a double exponential, and it became bounded. And the mechanism of the singularity is that the level sets of theta had a hyperbolic saddle, and the saddle seemed to be closing in at a fast rate, angle of the saddle. So here are some pictures of the paper of Peter and Esteban, in which it shows how the level sets of theta evolves in time. And then you can see, here's the saddle, the angle of the saddle starts closing, and as it closes, the level sets starts piling up, and the gradient of theta grows right there at a very fast rate. So my thesis in 1997 consisted in studying this scenario, and I obtained a quadruple bound on the growth of the gradient of theta, and then later, in collaboration with Charlie Pfefferman, we reduced this quadruple exponential to a double exponential. And since I don't know of any numerics that gives higher growth than this one, this is the most singular numerics that I know on SQG. Okay, so global existence. So if there's no evidence of singularities, let's see what can we say about global existence. So due to the Laplacian, the square root of the Laplacian. If we take a solution which is radial, that will give us that the nonlinear part will vanish, and that means that radial solutions are stationary solutions for SQG. And in 2011, Dritschel constructed a non-trivial family of rotating solutions which have C1/2 regularity. These, the way he constructed is that he went to 3 dimensions and constructed an explicit solution, which is an ellipsoid, and this ellipsoid rotates, and when you project it to the 2D, it gives you a C1/2 regularity. Okay. Then in 2016, in collaboration with Angel Castro and Javier Gomez Serrano, we constructed another family of global solutions. This family is C2 and completely supported, is inside here in this region, and theta takes the value 1, and outside it takes the value 0, and in between we have the level sets, and they pile up in such a way that is C2 theta. This is a solution which is very close to a radial solution, and it has a 3-fold symmetry. And these solutions exist for all time, and what they do is that they rotate at the constant velocity without changing the shape. Okay. And this distance is very small, but it's like 0.01. Okay. And it's a 3-fold symmetry, but I think we believe this can be done for any m-fold symmetry. And the reason which is not done, we have not done it, is that it's a computer-assisted proof. So we do it for a specific structure. And in order to check each m-fold, one has to do m times computer system proofs. Okay. Then in 2017, Gravejat and Smets, using a completely different approach, proved the existence of traveling smooth solutions, and Ao, Davila, Del Pino, Musso, and Wei prove a different scenario, different structure, also traveling and rotating solutions, which are smooth. Okay. Okay, so these solutions in which we know there's global existence, they actually don't have any growth on any norm. They just they preserve the structure, but they rotate or they travel. So are there solutions where we have growth of HS or C2 or the Helder norm, C1 gamma? And these are the results of Kiselev, the first one with Nazarov and the second one with Key, 2012 and 2021. In the first result, he showed that there exist initial conditions with arbitrarily small norm in HS, S bigger or equal to 11, that become large after a long period of time. Okay, so there's growth in the HS norm. And the other result has to do with the C2 norm and the Helder norm. In both cases, the C2 norm is the supreme is bigger or equal to an exponential times kappa. Kappa depends on the initial data times capital T. Okay, so given capital T, you can find an initial data that at capital T, this C2 norm is bigger than the exponential times kappa times of kappa T. Okay? And same thing with the C1 gamma norm. Okay. Okay, so now I'm in position to state our theorems, and this has to do with instant blow-up. So we consider, let's say, we're going to first, I'm going to consider solutions in CK. So given a constant C sub 0, a constant T star, and let's take K to be any integer bigger or equal to 2, then there exists an initial data whose CK norm is smaller than or equal to C0. This initial data belongs to the space HK plus 1/8 intersection with CK. So that means K is bigger or equal to 2. So we are in the space in which the problem is locally well posed in that space, such that there is a unique solution in this space, HK plus 1/8, that satisfies that for T is strictly bigger than 0, the CK norm has diverged instantly. Okay? And now these solutions exist for a time as in between 0 and T star. So they live for as long as you want. And initially, the CK norm is as small as you want, and at T bigger than 0, it diverges. Okay, so this means that the CK norm is not, you if you start in the CK, you're not locally well posed. This is not only is strong ill-posedness, but it's non-existence. Okay? And in the case of HS, we have a similar result that says that, let's say we are in an HS where S in between 3/2 and 2. Remember that this is the SQG is locally well posed for S is strictly bigger than 2. Given any constant T sub 0 and in any constant C sub 0 bigger than 0, there exists initial data that whose HS norm is smaller than C sub 0, so we can make it as small as we want, such that the solution for any T bigger than 0 has diverged. The HS norm has become infinite. These solutions exist in this norm over here for alpha 1 in between 0 and 1/2. So summarizing, these solutions are in H3/2, and they exist in H3/2 as long as we want. So initially they start in HS, S between 3/2 and 2. In this norm, they are as small as you want. And for a short time, they exist. They blow up instantly in the norm HS, and they exist. These solutions exist, and they are unique in the space H3/2 for as long as you want. Okay. Okay. So this says that the supercritical and Sobolev norm. And in CK, there's no local well posedness, and there's instant blowout. Okay. So in order to put this in perspective, let me introduce the generalized SQG equation. So this is just to interpolate in between 2D Euler equations and SQG. And we can even make it more singular. So we are going to take a power of the relation between theta and the string function. We're going to add an alpha over 2. So when alpha is equal to 0, we have 2D Euler equations where theta plays the role of the vorticity. If alpha is equal to 1, we have SQG. And if alpha is equal to 2, this just becomes that theta is equal to the stream function. So therefore, the nonlinear term disappears, and we have stationary solution. Okay, so for alpha smaller than 1, the equations is more regular than SQG, and for alpha bigger than 1, the equation is more singular than SQG. This system is locally well posed in HM for m bigger than an m tilde that depends on alpha. So when alpha is equal to 1, this m tilde is 2. And when alpha is equal to 0, m tilde is 1. But it's also locally well posed for more singular, all the way up to 2. And global well posedness is open for all the range of alphas between 0 and 2, excepting 0 and 2. Okay, so is locally well posed in HM and HS. What about Helder norms? Well, Helder norms is what we know is that is locally well posed for all the range in between 0 and 1, including 1. And in the case of alpha equal to 0, you have 2D Euler and you have global existence. What about CK? Well, CK is locally well posed for alphas in between 0 and 1, not including 1. And what we prove is that 1 one cannot reach 1 for locally well posed. So SQG actually is the critical equation for the locally well posedness of CK. So in the case of more singular equations, alpha in between 1 and 2, Kiselev and he showed that there exist solutions, initial data such that it grows faster than an exponential of t. And what we're working right now, work in progress, maybe at the end of April, we will have a paper in the archives where we actually prove that there is instant blow up in the case of this Helder norms for alphas in between 1 and 2. So, so again, SQG is critical in the case of Helder norms. Okay, so now let me give you the ideas, the main ideas and strategies to prove these theorems. And let me go. So this goes back to the work of Bourgain and Lee, El-Hindi, Mahmoudi, and El-Hindi and Jiong. for 2D Euler equations. So in the case of 2D Euler, so Laplacian, here we have power 1. What they prove is that the velocity is, and the 2D Euler equation are strongly imposed for the velocity in CK. Before I was talking about the vorticity in CK. And what they prove is that the velocity is strongly imposed in CK for k bigger or equal to 1. And the vorticity is strongly imposed in H1. Okay. They actually obtain stronger results in which they prove that the essential supremum of the CK norm of the velocity diverges. And in the case of the vorticity, the H1 norm diverges. And the main idea of the proof is when you write down the equation to the Euler equations, you have the pressure. The pressure, we can recover the pressure from the velocity by taking the divergence of the equation. And we have then that the Laplacian of the pressure is equal to this nonlinear term, which is the sum of the product of the derivatives of the velocity. So now we go back to the equation. We take the evolution, we take the gradient of the equation, and we look at the evolution of the gradient of u. We pick up two nonlinear terms that comes from taking the gradient of the nonlinear terms, and then we pick up two derivatives of the pressure. But since the Laplacian of the pressure is written as the sum of the products of the gradients of u, this can be written as a singular integral operator, the double Riesz transforms of the product of the derivatives of u. Okay. So this is a singular integral operator. So we can actually construct velocity fields whose gradients are very small, but whose singular integral operator is as big as we want, because the singular integral operator does not conserve L infinity now. Okay, so we take something that is very small, we look at its evolution, and we have something that is very big. Okay, this is in a nonlinear terms, and what we expect is that this nonlinear terms does not kill this growth. This is the idea. Okay, but it sounds simple, but it's not always true. Let me give you an example. So let me look at one dimension. If we look at this linear equation, which is a function, the derivative with respect to time is equal to the Hilbert transform of the function, say f, the usual definition of the Hilbert transform. This linear PDE can be solved, and the solution is given over here. So at time t equal to 0, this is not here, and we have f of x0. But as time evolves, time is strictly bigger than 0, then this sign t comes up and is multiplying the Hilbert transform of f. And the Hilbert transform of f, we can take something, some function f which is small, whose Hilbert transform diverges. So this is the example of the mechanism what we're looking for. Okay, so let's add a nonlinear term to this 1D. And the nonlinear term is this f times the derivative of f. Okay, this equation is known as the Burger-Hilbert equation. If the Hilbert transform is not there, right, it's 0, then the infinity norm of F is conserved for sufficiently smooth solutions. But if we have the Hilbert transform, what this is work with Angel and Paco, 2010. Then the second derivative of the L-infinity norm of F satisfies this inequality over here, which tells you that you can cook up an initial data in such a way that the L-infinity norm blows up in finite time. Okay, but this is true. This to obtain this inequality is true as long as the solution remains C1 gamma. Okay, so as long as the solution is smooth, then your L-infinity norm grows very fast, and if nothing stops it, it diverges. Okay, we were very happy with this result because we thought this was singular integral operator was giving us a mechanism to prove finite time singularities. Then 4 years later, Rezan and Nguyen prove that the L-infinity norm does not blow up for Burger's Hilbert equation. It remains bounded, and it's a uniform bound. This does not contradict this one, because this is true as long as the solution is C1 gamma. So what this is telling you is that the C1 gamma blows up before it reaches the bound that they prove that the L-infinity norm has. Okay, so this is an example in which you have an equation of evolution with a singular integral operator. You can take the singular integral operator to be as big as you want, and the nonlinear term kills the growth. Okay, or something else happens before. Okay, so SQG. So for SQG, El Hindi and Mahmoudi in 2020 used the ideas that they did for 2D Euler equations, and they applied it to SQG, and they took a perturbation of a stationary solution as G of X2, and this perturbation satisfies this equation of evolution, where you have a nonlinear part, right? And this is linear, but is one derivative transports. It's a transport term. But on the right-hand side, you have a linear term, which is a singular integral operator, and is the first Riesz transform of the perturbation. G prime is given. Okay, so what they prove is what is known as a mild ill-posedness result, which says that there exists a constant C bigger than 0, which is proportional to the infimum of G prime, and a initial data theta epsilon, which is C infinity, whose norm W1 infinity is as small as you want, that at time 0 and at time t, and t is as small as you want, the W1 infinity is bigger than C. Okay? This is for the perturbation, not for the solution. Okay? This is what is known by mild ill-posedness. If instead of C, you have 1 over epsilon, then that means strong ill-posedness. Mild ill-posedness does not imply strong ill-posedness. For example, for 2D Euler, it's easy to prove that the CK gamma is mild ill-posed. The perturbation of stationary solution of 2D Euler is mildly imposed in CK gamma, and we know that there is global existence in CK gamma. Okay, so we need a different approach. So the way we prove a non-existent instant blow-up for CK is the following way. The proof is divided in 2 steps. In the first step, the goal is to prove strong ill-posedness, which means that given a T star strictly bigger than 0 and a constant capital M, then there exists a solution theta of xt of SQG that initially the CK norm is as small as you want, but at time T star, the CK norm is big or equal to M. Okay? In order to prove this, we are going to take a perturbation of a radio solution. Okay? And we call the perturbation theta pert. This is going to be our initial data. And we define a pseudo solution. What we say is a pseudo solution is a function theta bar that satisfies SQG equation with a source term, capital F. And the source term is in certain norms as small as we want. If we have that property, we say that theta bar is a pseudo solution of SQG. Okay, so we take our solution theta, a perturbation of a radial function. We plug this in SQG, and what we have is we obtain 4 terms, the derivative in time. This is the velocity in the angular component, is the angular component of the velocity, and UR is the radial component of the velocity. And here we have the nonlinear term. Okay, so we get rid of the nonlinear term, and we keep the remaining terms. And the solution of this equation is theta tilde. Now we are going to, this is one way to approximate the equation. And since we are going to make another approximation, which is F is our stationary solution. So we are going to take that the derivative of F with respect to R is like a constant C sub 0. And the velocity of theta tilde in the radial component of the velocity, we're going to take it to be the Hilbert transform of, instead, the radial component of the velocity is a composition of the Riesz transforms, singular integral operators in 2 dimensions, and we are going to approximate it by the Hilbert transform taking in the angular component. Okay, and that's going to be our new term. Okay, now for this system, we can obtain a specific, we can solve this equation, and the solutions of this equation is exactly this functions. A function that depends on R and the signs of a constant capital N times the angular component minus T times capital N, the angular component of the velocity divided by r with this constant c sub 0 times t. This solves this equation. This equation is linear. So I can sum as many as I want of this sort. And I can multiply by constants. So my solution, I'm going to take a function, this function, which is going to be this term, lambda, is a function, sorry, it's a function that depends on three constants, lambda, capital K, and capital N. The radial component, the stationary solution, is lambda times f of 1, which depends only on r. And this is a function which depends only on r. And then the sum of signs of this type. Okay, multiply by these numbers. Okay, so I call this theta bar. This theta bar satisfies this equation. Okay. Why do I pick this these constants, lambda k, and n? And I pick those because this, when you compute the C2 norm at time t equal to 0, this is smaller or equal to C lambda, a constant times lambda. And this constant is independent of k and n. If you look at the h2 plus 1/4 norm at time t, is bounded by C lambda k, where C is independent of lambda k and n. And if you look at the C2 norm of this function at time t, this is bigger or equal to a constant times lambda squared times lambda k times t. So we can make the C2 norm grow by taking capital K as large as we want. And we can take lambda to be as small as we want to make the C2 norm as small as we want. I'm looking at the C2 norm now. Okay, so this is the properties that this function satisfies. Okay. Now we plug this function in the SQG equation, and we get a source term, an F, a capital F. And what we show is that by taking specific F1 and F2, these F1 and F2 will be radial functions that are supported in an annulus, and they have certain properties. And under those properties, one can show that the source term is bounded in L2 by this quantity. So by making capital N as large as we want, we can make the L2 norm small. The H3 norm grows a lot by taking N large, but the H2 plus 1/4 becomes small as we take N big. Okay, so, and these constants depends on lambda, K, and capital T. So give me capital T. Give me lambda. Lambda tells me how small the solution is. Capital K tells me how big the C2 norm grows. Given those numbers, I can find a capital N in such a way that F is, in certain norms, small, and our, well, okay, and all these bounds are true in this time interval. These solutions are smooth. They are C infinity. Okay, so now we take the difference between this pseudo solution with an actual solution of SQG, and using the properties of the pseudo solution, we can prove that the difference in L2 is controlled by capital N, and the H2 plus 1/4 norm is also controlled by capital N. So, and so that gives us a solution of SQG that remains in H2 plus 1/4 as long in the time interval between 0 and capital T. And the C2 norm grows like lambda K times T. Okay, so this is strong ill-posedness. But we want to, and okay, so this is the case of C2, and for CM, we just have to add these powers over here of this constants. Okay, and that gives us a control of the sorter of this in this way. Okay, so now to go from strong ill-posedness to non-existence, what we're going to do is to add infinite of these solutions. We are going to put these solutions in oh, this is not okay. So we are going to put one of these solutions here, another one here, another one here, at different distance. And we are going to add infinite of those. Okay. Each of them are going to have their own constants. We pick up the constants in such a way that each of them has this behavior. These solutions are compact, so they are at a distance from each other. And we control this distance. If you add infinite of them, at time 0, your C2 norm is as small as you want, but as time is strictly bigger than 0, your C2 norm has diverged in finite time, and your solution remains in H2 plus 1/4. Okay, so that's how to prove instant blow up. Now, in the case of HS, and time is almost over, let me be brief. The strategy is the same, but we need a different scenario. We need a different perturbation. And the perturbation in this case will take this form over here. And we need a different scenario because what we want to grow very fast is the HS norm. And we prove strong ill-posedness in this for this perturbation. And then to go from strong ill-posedness to non-existence, we add again infinite of these solutions, which are at certain distances. But in this case, the proof is more involved because we are in a much lower regularity, and we are below H2. And for this, one has to use a fixed point argument to show that your solutions are actually in a space which is a little bit better than H3 has. Okay. And what happens, and this is my last slide, in the case of H2, the critical case? Well, in this case, the previous scenario does not work because is critical, and uh, and we need a different approach. And here we use the scenario of Bourgain and Lee, which has this form over here. And here we are not able to prove, say exactly how the solutions look like. And what we can prove is the strong ill-posedness and that this essential supremum diverges in a small interval in time. Okay, so um, uh, 2 days after we posted our paper in the archives, Inji Jong and Jung Ha Kim posted an article in which they prove strong ill-posedness and non-existence in this way for the H2, for the critical space H2 for SQG. And with this, I finish. Thank you.